there, kids. Welcome to Notes with Me. This is a rapid review on work and energy. All right. Introduction is that an object has kinetic energy by moving. Interactions can create potential to do more work. And work is done when a force acts parallel, and work can change the kinetic energy of a system. Let's write those down. An object has kinetic energy by moving. We say that interactions with other objects or force fields for that matter can create the potential to do work. Potential energy. We say that work is done when a parallel force acts over a distance. Let's put bullets here. And I'm getting a lot of this from 5-2 a 5. It's an AP like prep textbook from 2014. Well, the examples anyway. We also say that when work is done on an object or system of objects, kinetic energy can change. All right, let's get into more details. Speaking of different energies, let's start with kinetic. Kinetic energy, we think of the word motion. We have translational and rotational. Right, so K-E-T and K-E-R, or rot, or trans. 1/2 mv squared and 1/2 I omega squared. Translational kinetic energy exists when the center of mass is moving. And rotational kinetic energy exists when an object rotates. More fun on that later. Next up is potential energy. This is stored by position. In this course, we're looking at a couple kinds. One of them is gravitational. It's either PEG or UG, and it's equal to MGH. This is stored in a gravitational field near a planet. We also have PEG negative G M1 M2 over D when it's far away from a planet. And this distance is from the planet's center of mass. It's not a typo. It's not supposed to be d squared. Remember, because we have f of g is g m1 m2 over d squared. And work is fd. So that's where the other d on top comes from. Cancels them out, and you get that one. Work is energy. See it? The other one is elastic. PES for spring, or US for spring, and that is 1/2 kx squared, stored by a spring. And remember, that has a restoring force, negative kx. Another is internal energy. And the whole idea with this is just to make the point that multi-object systems can store energy depending on how the objects are arranged. Multi-object systems can store energy depending on how the objects are arranged. I hope that made you think of states of matter. So this gets broken down, but mostly when we go microscopic, we talk about microscopic internal energy. We are really talking about temperature. Stored in the vibrations of molecules. And if you ever come across something like internal energy of a two-object system, I just want you to know that's just super fancy words for potential energy. Okay. 3 more players in this game. We've got mechanical energy. This refers to the sum of all potential and kinetic energies. Work. Work is done when a force acts parallel. Well, that sounds weird. Let's say work is done when a force acts on something. Yeah, now we're talking. That moves a distance parallel to that force. Power is just energy used per second, how fast you can do the work. And that's P is work over time, measured in watts. So like 1 watt is 1 joule, 1 second. Remember that spring and cart? Investigation? We had a ramp, we had a table, we had like a stopper, there was a spring, there was a cart. We compressed the spring and then let it go, and zoom, the cart went up the hill. And we were able to measure how high it went. And in that lab, I was looking for folks. Not everybody regraded this one, so now's your chance to pay attention. You would measure it from the center mass of the cart, or at the very least, the same point each time, right? Because we have height off the table, and then we have change in height. So be sure, say it stopped right here. Be sure you're looking at change in height, right? Not just total height. You guys had some other savvy ways of doing that, as long as you're consistent. Let's look at the energies here. We've got we have initials and finals. We've got spring potential energy. We've got gravitational, and we've got kinetic. Okay, initially the spring potential energy is maxed, and the gravitational potential energy is 0, and the kinetic energy would also be at its max, and then zoom, it goes up to the top, and the spring potential energy is 0. The gravitational potential energy is maxed, and when it stops moving, its kinetic energy is 0. Now, right when the first thing happens, we've got all this potential energy stored in the spring that gets transferred into the initial kinetic energy. And that's at its max right there. Okay, and that's the first thing that happens. The second thing that happens is that this gravitational potential energy gets transferred. Well, I wouldn't say that at all. I would say it comes from here. Sorry, my arrows. It goes from the max kinetic energy to the max spring. Yeah, that makes more sense. The mechanical energy is the sum of all the kinetics plus the sum of all the potential energies. All right, let's look closer at work. Work is equal to F delta X in the parallel direction. Fx cosine theta is another way we looked at it. Fd cosine theta, same thing. For example, there is a box and a string. Let's pull the box. A string applies a 10 Newton force to the right on a 2 kilogram box, dragging it at a constant speed. Ooh, that's going to be useful. Across the floor, a distance of 50 centimeters. All right, so free body diagram, review. We've got our box, and I'll draw the weight. Normally this is force due to gravity, F sub g, but let's call it W this time. And it's not accelerating vertically, so I'm going to draw the normal force, equal and opposite. We've got a tension force pulling to the right. And since it's going at constant speed, I know it's not accelerating, and therefore the friction arrows should be drawn equal and opposite to the tension. And if it's not obvious, you can of course tag so you can see who's equal to who. Okay, so let's do two things. Let's find the work by each force, and then we'll look for the net work. Let's see if we can get all that. Okay. All right. Well, let's look over here. We've got tension equal to 10 newtons, and it's dragged for 0.5 meters. So the work done by tension is a +5 joules. Let's look at friction, negative 10 Newton for 0.5 meter. So the work done by friction is negative 5 joules. Now I bet you know the work done by the vertical forces based on the definition of work. But if you like math, you can also look at it that way. Let's keep going. We've got the weight is 20 Newton. I guess that would be negative in my book, right? 20 Newton for 0 meters. So the work done by the weight, a lot of W's, is 0 joules, just using math. And the normal force is equal and opposite, but let's do it anyways. 20 Newton for 0 meters. So the work done by the normal force is also 0 joules, plus these are not parallel. So could have answered it that way as well. Alrighty, how about the network? That was number 1. Number 2. So we can use a free body diagram, or we can use algebra. If we use a free body diagram, we can simply show that we've got 5 joules to the right and negative 5 joules to the left. We can also say that negative 5 plus 5 is equal to 0 joules of net work. Mostly because this word constant, it's a giveaway. All right, more detail on conservative and non-conservative forces and how they apply to work energy theorem. Let's say a conservative force converts potential energy to other forms when it does work. And does not change the mechanical energy of the system. In this class, there's only 2 conservative forces you're playing with. So in APP1, those 2 forces are gravity and springs. Only at this level. So when a spring does work on an object, energy is stored in the spring that can be recovered and converted back to kinetic energy. When a spring does work on an object, energy is stored in the spring that can be recovered and converted back to kinetic energy. The sum of all the potential and kinetic of the object spring system is constant. Okay. Work energy theorem and a case study of an archer coming up next. Okay, last point. This is like a case study here, but it's to review the work energy theorem and push us a little farther. We're going to look at an archer. So here's the story. An archer pulls an arrow, pulls back an arrow, I guess. I have an archer pulls an arrow of mass 0.10 kilogram attached to a bowstring, back 30 centimeter by exerting a force that increases uniformly from 0 to 200 newtons. This example is also from 5205. So let's see. First thing I want to do is to categorize the problem. There are 3 ways to approach mechanic problems. Right? We've got kinematics and Newton's laws. We have momentum and energy. Those are your choices. I'm pretty certain that all the problems you're going to come across in this course, at least on the AP test, or, you know, these are the 3 things you can do with them. So let's look at this problem. It's not a collision, so it's not momentum. At least not the part about, I guess it would be a collision after the arrow's released. You can make some claims about collisions then, but we don't have that kind of information anyways yet. Oh, but we could. Super problem. Nonetheless, not a collision, so not number 2. It does talk about force, but, and this is very important, it says a changing force. So kinematics are out. That leaves us the work energy theorem. Okay? Second thing I'm going to do is identify the type of potential energy. Remember, it's either a spring or gravitational. So let's see. It's not a spring. And it's not gravitational. Oh my gosh. Oh no, I don't know what it is. Well, make a choice. Which one is it more like? It's more like the spring. It's got a restoring force. Okay. Here's a couple questions we could play with. Question number 1. How much work does the archer do in pulling back the bowstring? Okay, most of you will be tempted to say, oh, okay, work is force times parallel distance. No, don't do that. Can't do that. Since F is changing, this equation doesn't apply. Okay, you have to use the work energy theorem. All right. Let's look at non-conservative forces. All right, it's more fun because it's going to change the mechanical energy of the system. So that's going to be change in KE plus change in PE. And in this course, well, actually, most of it, well, I wonder if I can think of another one. Either way. So the kinetic is always going to be your translational kinetic energy plus your rotational kinetic energy. Okay, and your potential is going to be gravitational, or this is a plus, and this is an or spring. Nice little, remember that. Okay. Nonetheless, if they ever ask for network, that is still the sum of the work done by conservative forces and the work done by non-conservative forces. But anyways, all right, hang on, let me turn the page. Okay, so we've got the work done by non-conservative forces will be equal to the translational kinetic energy, which is nothing because it starts at rest and ends at rest. There's nothing rotating, so that's a 0. Plus change in spring, right? So we'll just have 1/2 kx squared plus, minus 0. It starts with 0, and then it goes. Okay, let's say the U of the spring is 0 at equilibrium and max at full extension. Okay, let's make some notes on the side. The work done by the archer is non-conservative. Since it changes the mechanical energy of the string arrow system. Okay, all right, we've got X at 0.30 meter. We don't know K, but we know it's a restoring force. So we can use Hooke's law and rearrange it for K, negative F over X. We have 200 Newton, negative 200 Newton divided by negative 0.3 meter, and that's 670 Newton meter. So now we have K, nice. Work done by the archer will be 1/2, 670 Newton per meter, times 0.3 meter squared, 30 joules. I love when it comes out to a whole number. I feel like I did something right, you know? All right. Here's another question. Same storyline. If the archer pulls back 60 meters, well, not 60 meters, sorry. That would be crazy. 60 centimeters. What happens to the work? All right, well, we're looking at 1/2 kx squared. It's not same. We've got a squared here. So when x is doubled, 4 times the work. Love that pattern. There's another question. A more interesting question. How fast does the arrow go after it's released? So we can still use the work energy theorem, but we're going to shift our timing for our initials and finals. We're going to look at a different interval of time in that situation. But this time, look at when they release the bowstring to when the arrow is released as the string goes back to equilibrium. Okay, now what? Well, we know the network is 0. And we have, it goes back to equilibrium, so it goes back to 0. 1/2 mv squared plus 1/2 kx squared, minus 0, right? Essentially, we're having all the bow stored energy in the bow convert to kinetic energy of the arrow. We know that we're going to have 30 joules. That's what it's supposed to equal. 1/2 mv squared. And you get a V of 24 meter per second. That's nice and fast, but not too fast. So we're going to go for it. All right, take some time to go over the details in the last bit that I showed you and maybe fill in some steps that you need. Or just take some pics and send them up on Canvas. You guys have a great night, and thanks for taking notes with me.